Okay, let's dive right into this explainer. We're looking at the absolutely incredible engineering and the massive stakes involved in transforming raw crude oil into the exact fuels that power our world. We use these fuels every single day, right? Usually without a second thought. But the process of actually creating them, it is a total marvel of extreme heats, immense pressure, and literally microscopic chemical warfare. But before we get into the triumphs of all this engineering, we really have to start with a pretty stark reality. Every single distillation tower out there is essentially a controlled bomb. And this was tragically illustrated by the 2005 Texas City disaster. If you look at the timeline here, it all began with just one single faulty level meter. A tower that normally holds about 7 feet of liquid quietly filled up to an astonishing 158 feet overnight. The pressure broke, a massive vapor cloud escaped, and a nearby idling diesel pickup truck actually sucked that vapor in, over-revved, and ignited the entire cloud. Now, what's really interesting and honestly terrifying is the sheer scale of that number. When that 170-foot tower overflowed, nearly 2 million liters of hot, highly flammable hydrocarbons escaped in just 6 minutes. To put that into perspective, the resulting explosion tragically claimed 18 lives, injured over 185 people, and burned a 200,000 square foot area completely to ash. It's a very sobering reminder of the raw, immense power we're dealing with here. So, the absolutely crucial point is how we safely operate these massive, high-pressure systems. And we're going to uncover that by tracing a single drop of crude oil through this precise 5-step journey. Preparation, the main distillation tower, working under a vacuum, cracking the heavy molecules, and finally, treating and final blending. Let's get into it. Step 1. Preparation. Before we can even think about separating the valuable fuels from the crude oil, we have to relentlessly clean it. We've got to remove water, salts, and sulfur compounds that would just instantly corrode the pipes or completely clog up the costly catalysts downstream. And honestly, this perfectly illustrates the elegance of refinery engineering. Instead of using some complex, expensive chemical filters, engineers do something incredibly simple. They just mix the dirty crude oil with clean water. Then they apply an electric current to the whole mix. This static charge forces the tiny salty water droplets to attract each other. They merge, get heavy, and just drop right out of the bottom of the tank. It's so simple, but it's highly effective. Okay, so after the salt is gone, the oil gets pushed through a series of heat exchangers. Now, before it even hits the main furnace, it enters what's called a pre-fractionator at around 180 to 200 degrees Celsius. At this relatively mild temperature, the easiest 5 to 10% of light gases vaporize right off the bat. This pulls out valuable LPG and raw naphtha early on, which lifts a massive amount of the load off the main furnaces and leaves the bulk of the oil perfectly primed for the main event. Which brings us to step 2, the main distillation tower. Now we're moving to the absolute heart of the refinery. The main fractionator, or crude distillation unit, is where the real magic of separation happens. To unlock the rest of the oil, these massive furnaces use roaring burners to blast the crude to a blistering 360 degrees Celsius. Once it hits that extreme temperature, the superheated crude is injected directly into the flash zone of a massive distillation tower that can stand up to 200 feet tall. Now, what's really fascinating here is how temperature gradients physically sort the vaporizing oil. As the vapor rises up this giant tower, it naturally gets cooler, so different molecules condense back into a liquid at different temperatures. This means the lightest gases, like fuel gas, fly all the way up to the top trays. Right in the middle, you get your naphtha, your kerosene, and diesel. And down at the very bottom, the heaviest liquid residues just kind of fall down. Basically, the tower naturally stacks the fuels by their weight. But, the system isn't perfect. Sometimes heavy molecules get carried up into the lighter liquid pools, or light molecules get trapped down in the heavy ones. As the source material humorously points out, these wandering molecules are a lot like politicians changing parties. So to fix this little issue, engineers use side strippers. They inject superheated steam to basically chase those wandering light molecules back up the tower to exactly where they belong. All right, step 3, working under a vacuum. Even after applying that intense 360-degree heat in the main tower, about 30 to 40% of the crude oil simply falls to the bottom as this thick, heavy residue. And that poses a massive chemical challenge for the engineers. You see, heating that thick residue any further to extract more fuel wouldn't work. It would just burn it into useless solid coke. So what do? Engineers deploy a brilliant physics trick. Using the Venturi effect, they blast high-speed steam through a constricted tube at the top of the next tower. This physically sucks the air out and drops the atmospheric pressure inside to nearly zero. Operating in this intense vacuum, we're talking dropping the pressure down to an incredibly low 10 to 15 millimeters of mercury, means this stubborn residue can suddenly boil and separate without needing any destructive extreme heat. This vacuum distillation allows us to safely extract heavy gas oils from the mix, leaving behind only the absolute bottom of the barrel residue, which is exactly what we use for paving roads with asphalt. Moving on to step 4, cracking the heavy molecules. So what do we actually do with all those heavy gas oils we just managed to extract? Well, we're left with these massive, clunky hydrocarbon chains that are just too heavy to burn in a regular car engine. So they literally have to be chemically shattered to become valuable fuels. Here we can look at our 2 chemical sledgehammers used to break these chains. First up is fluid catalytic cracking, or FCC. This shoots the heavy oil up a 25-meter vertical riser mixed with a blistering hot sand-like powdered catalyst. In literally 2 to 3 seconds, that catalyst rips the carbon right out of the long chains, breaking them apart. The second method is hydrocracking. This one crushes the oil using immense pressure, like 160 kilograms per square centimeter, all while flooding it with hydrogen gas. Out of those 2, the hydrocracker is essentially the VIP of the refinery. In fact, the source actually calls it the prime minister of the equipment. Because it uses that extreme pressure and hydrogen, it forcefully extracts sulfur and nitrogen like it's exterminating pests. The hydrogen bonds perfectly with the broken chains, leaving behind premium, perfectly clean straight-chain BS6 standard diesel. And finally, step 5, treating and final blending. Okay, so we've distilled, we've vacuumed, and we've cracked. The final stretch of our journey takes those newly created raw fuels and chemically polishes them to meet precise, strictly regulated market standards. Take raw petrol, for example, which comes from the naphtha we separated earlier. To make a really high-performance petrol, we need a high octane number. This simply means the fuel won't randomly explode under the intense pressure of a car engine's piston before the spark plug actually ignites it. If it ignites too early, you get what's called engine knocking, and nobody wants that. So, to boost that vital octane rating, the refinery sends the naphtha to the isomerization unit. You can think of this unit as a molecular shapeshifter. It doesn't break the molecules. Instead, it literally bends weak, straight-chain hydrocarbon molecules into highly efficient branch-chain molecules. It completely changes their physical shape so they perform better inside your car's engine. Pretty amazing, right? Finally, the whole shebang comes together. Fuels from the fractionator, the crackers, and the treating units all meet in the massive blending pool. Here, treated naphtha, pristine diesel, and specific additives are mixed together exactly to local market specifications. This ensures the fuel performs perfectly whether you're driving up in the freezing mountains or out in a scorching desert, all before it ever hits the pump. As the source material so beautifully summarizes, refining isn't just about boiling oil. This intense gauntlet of heat, pressure, and advanced chemistry is really all about unlocking the astonishing variety of hidden treasures buried deep inside crude oil. It's about turning that dark, raw sludge into the everyday products that literally keep our global economy moving. So the next time you hear your car engine start up and you feel that immediate forward thrust, I challenge you to think about the towering infernos, the extreme vacuums, and the microscopic chemical warfare that was required just to give you that power. Will you ever look at a gas pump the same way again? Thanks for joining me on this explainer, and keep questioning how the world around you actually works.